welcome back to our math teaching and learning online today again. Today is very beautiful day. I would like to look at through the beautiful natural view outside my window. I live in such a God bless area. It's so beautiful. It's breathtaking. It makes my heart just feel feeling peace and nature, fresh air, nature. Anyway, um, I'm happy today to get back to our online um, because I was so busy with the setting up my new website, and it's a beautiful website. So I would like to introduce to you. So on my board, if you go to Google and you key in my math teaching dot, see the website. I just view it, wordpress.com. Because I just build it, just constructed. So there are not a lot of stuff in there yet, but eventually I will post some beautiful video in beautiful website. You might be interested in it. You might take a look, check it out, right? So I was so busy to set up my lesson plans and still working on developing the second course in Introduction to Calculus online. This is I believe this is the third or fourth lesson in the unit 2 of the Introduction to Calculus course 2. It connects to the previous lesson I was talking about the equilibrium system. So in our lesson today, I get into the application of this. I will show you how to solve an equilibrium problem. So bear with me for my totality, and allow me to, like sometimes I don't know how to shorten my teaching. I have to explain in a long way, and I wish that you be patient with me. Anyway, let me get right into the word problem, and I will read it out loud to you, and we'll show you how to solve it. So let's take a look at the board on the top of my head, and we'll read together. Solve an equilibrium problems. A spring with a mass of 1.3 kilogram has length equal 0.6 meter. A force of 20.8 Newton is required to stretch it to a length of 1 meter. If the spring is stretched or compressed to the length given, then released from rest, find a displacement function at the time t. Okay, so let me draw a diagram to demonstrate what the data given to us. So we have a spring, right? Say a bar here. We have spring. Now the spring have a length from here to here is 0.6 meter long, and then the spring was stretched. So this part is dotted, I mean like stretching, right? It's stretching another length of 0.4 meter to add up become 1 meter at this position level, right? So this is the position level. Now, it was stretched like this by a force, and I call this force is, using the arrow here, this force here equal 20.8 Newton. And why it corner, this is any force have a unit is a Newton unit. It's based on the Newton scientist, right? And he was really famous, just like Albert Einstein, famous for the E equal mc square, which is mass times the speed of light. And our Newton's famous for force equal mass times acceleration, right? So this is his equation. Force equal mass represented by m times a is acceleration. And in this equilibrium system, he explained that any force have a equal reaction force. So these two forces go different direction, right? One goes towards the left, one goes towards the right, and any force have equal reaction force. I was explaining this concept in the previous lesson, so I will not talk too much about that in this video. In this video, our purpose is to solve this problem. Okay, if you like to listen more about the equal reaction force, which I found is a fascinating topic, and I was talking a little bit about it in my previous video about the concept lesson of how does the equilibrium system work, and were explained and was developed by our mathematician with the equation and the formula, come up with the formula, right? So today we just use the formula because we already learned about it, and we already understand how the formula was developed. Now, usually students at this level, we don't need to require to solve a lot of proof. Sometimes, we are given a tough task to solve to prove it, but you just apply the formula and solve the problem, right? Even though that is take us a lot of time, and sometimes if we have a 20 student in front of class, not like online like this, we don't have time to teach the student how to prove it. Now, as the instructor, sometimes we need to show to the student the proof of it, so that we try to convince the student that, yes, where it's come from and how it's developed. Anyway, let's get right into the solving part today. So we have a force equal mass times acceleration. Now, this force, in this case, in this scenario, we can write like this: force equal K times S. Now, S here is just the position function, right? Of the velocity acceleration when the motion of the spring was stretching it down or up, right? And the K here is just like the index of the material of the body, right? So this force can be written like this. It also can be written like, remember, we developed from this equation, y prime, which is the second derivative, adding with ky equals 0. And this is the equilibrium system, right? Equilibrium system explain that any force have an action equal reaction force, different direction but equal in magnitude, and therefore it cancel out each other, and it give the system become 0, right, when it cancel out. And it's true, Now you notice that if you stretch the spring down, right, and then you release it, it go back up with the same distance, right? So that's the Newton's second law. And based on this, we have this differential equation. This is equilibrium system. And in my previous lecture, we're talking about, because if we have a derivative, this is the second derivative, right? D square s over dt. In our case, we can write like this. Adding with k divided by m is the mass of the body, time with the s function equals 0. Now, what I try to do, I forget. Okay, so we try to develop this equation and solve for it. And in the past, we say that we already proved it. After we solve this differential equation, right? We prove that if there is a differential equation like this, which is the stretch of spring respect to time, then there will be exist in equilibrium system, there will be exist an original function of y, right? And our original function of y, therefore, our y function, or we can say s function in this case, will be equal a cos square root of k. Instead of x is t, because we're talking about the respect to time, right? Adding with the b constant psi square root of k of t, right? And we come up with how this equation as it, this formula as it was derived from this initial equation. And I went through with you about how to develop this equation through by the videos, previous video. If you forget about it, you can rewind the YouTube and then watching it. If you register in my course, you can have access to on the lesson, the lecture notes, the beautiful MS PowerPoint presentation, and learn this course in a easy way, right? Rather than watching randomly from YouTube. But anyway, this is the formula we derived from my previous video. I just want to remind you. And now this formula was already accepted and proven by mathematicians and have learned by us, right? We're going to use this equation to solve this problem. So let's start with step 1. Now, in the step 1, to solve this problem, you need to find the k value. And our k value can be found from the equation of Newton's second law, right? F equal k times s, and we substitute the force is 20.8 Newton equal k, we want to know, and our s is actually, this s is the delta s. So delta s equal s2 minus s1. And our S2 is stretched to the length of 1 meter minus S1 is the natural length of the spring, which is 0.6 meter. And therefore, delta S here equals 0.4 meter. So we're going to substitute this by 0.4. So for k, we divide both sides by 0.4, right? And when we divide this will gone, right? And the k will be equal to 52 Newton. Actually, no unit, it's just the index unit. okay? So we have 52, K equal, now we know that. So now let's substitute in this equation, and therefore we say our S function will be equal A cos of our K is 52, but remember the formula is K divided by M, which is the K divided by mass, and our K divided by mass equal 52 divided by 1.3 kilogram, right? That's the mass. So then it will be equal 40 Newton. Equal 40. So we have square root of K, which is square root of 40, based on this equation, right? Times T, adding with B, sine of square root 40 times with T. Now, this expression is the position function. Keep in mind this S we're talking about is not a numerical value, but actually this is S of T, which is the function position respect to time. It's the function is not a numerical value. Now, we're just lazy, we don't want to put S of T, but that S is the function, right? It's like a Y function, okay? So now we're going to next step. We're going to say step 2, we're going to say phi A. And step 3 is phi B, okay? Now to phi A, we set the time. So at the time T equals 0, at T equals 0, the mass is at rest. So now to phi A, we're going to substitute T by 0. So our S will be equal, and actually we want to answer question A. And in the question A, we have to develop a formula or an equation of S of T using this data given, 0.7 meter. So our delta S in the question A is 0.7 meter minus 0.6 meter, the natural length of the spring. And that will give us 0.1 meter, right? So now we know delta S. So therefore, we can substitute 0.1 for the left side, 0.1 equal A, cos, follow the formula, cos of 40 times T, but the T here we'll substitute by 0, adding with B, sine of square root 40 times T, and the T here we set at 0 at the beginning. So now we solve for A. Now keep in mind cos of any 0 degree. If you learn trigonometry in Math 12, you know that this 0 degree, the same at 360 degree, same at 2 pi, right? And we have 0, we have 1, 0 here, and 0, 1 here, and 0, minus 1 here, and minus 1, 0 here. What does that mean? This, the first here is the coordinate of cos, and the next is the coordinate of sine. So if you remember the secant, right? In quadrant 1, cos here is 1. So cos of 0 degree equal 1. So this equal 1. Now sine of for 0 degree, right, equals 0. So 0 times with anything is 0. So the whole thing here just cancel, it becomes 0. So we left with what? This is 1 times with A. So A equal 0.1. So now we know this A. So now our job is next step. We already know A, now we find B. And to find B, we use the velocity, ds over dt. And our velocity, remember, at the time equals 0, the mass is at rest. So it means the velocity also equals 0. So therefore, we're going to substitute our ds over dt function. But let's first develop the ds over dt first, which is the same like derivative, right, of this function, s prime. And the derivative of this is minus square root 40 times with a times with derivative cos becomes sine equal minus sine. That's why we have minus here. Sine of square root 40t. Adding with, and let me erase this so that it doesn't look so messy. Adding with b, and derivative sine is cos. So adding with square root of 40 times b times cos of square root 40 times t. So this is our ds over dt, and we use it to solve for b. So now we're going to substitute the s prime here equals 0 because we know mass is at rest, velocity equals 0, right? So now let me put in the substitution in. So we have minus square root of 40a sine of 40 at time t is 0, adding with square root of 40 b cos at time of t here is 0. Again, this cos of square root 40 is 0 should equal 1, right? Because cos of 0 equal 1. So it means at this time, this second step, this expression, the whole thing equals 0. Because 0 times with anything is just 0. We left with this expression, right? However, we have a situation that 0 equals this as well. So it means b will be equal 0, right? So b will be equal 0. So now we know A, we know B, and our job is write a position function as a t respect to time when the spring is stretched up to this much. So our function now has been developed so far all the way from here to here will be s of t equal our a is 0.1 in this particular scenario, right? 0.1 and our function back in the position function, right? This formula, cos of square root of 40t. Now, do we have this second section? We don't, because we say b equals 0. So if b is 0, you substitute in here, 0 times anything is just 0, so why bother? So it means this is the equation we just developed. Now, keep in mind that, remember, this is the solution for this particular question. In another equilibrium system, in another scenario, if we are given a different data, we might not have the answer like this, even though we went through the same formula. But when we solve, we might end it up with, yes, we do have the second part here, including the first part here, just like that. And maybe our A is different number from our B or something like that. Depend on the system, right? And the data we are given when we solve the problem. But at least I give you a hint. I established my um, explanation and show you how to solve the problem step by step. um, we call it instructional teaching method. And I found in mathematics, instructional teaching method is the most powerful structure. And we have different teaching method. We have constructivism. We have different from different philosopher of education provide us constructivism, which is you learn based on the piece of puzzle, you put it back and construct it, right? And you come up with your new idea and your new own explanation rather than to be instructed by the instructor. Now, each method have its own advantage and disadvantage, right? In history, in geography or language course, the constructivism might be a very powerful tool to do that. And as a teacher, you can apply on the methods of teaching together. So if I am an instructor in the public school like before I did in private education in my classroom, I use all of them. Someday I use instruction methods, and in math we cannot lack of that. That had to be a it, because if you don't have a instructor to show you step by step, how you going to be able to understand it? Sometimes you invent it, you think, you imagine beautifully, creatively, but maybe your imagination or your creativity isn't correct. And in math, there's only one correct answer. Now, in language course, I was not talking about that, right? Sometimes the vocabulary we develop is came from the newborn vocabulary and thing. Now, each course have its own nature differently. Math have its own universal language, also is structurally. So therefore, instructional method in teaching math is so powerful tool to provide most student, uh, general student, right? The right way to approach. And even though in music, in ballroom, I found you cannot create if you lack the basic foundation. Like if you learn accounting or bookkeeping, you have to learn the basic stuff before you can put in the QuickBook software and figure out using on the Excel spreadsheet. But if you don't learn the basic, hand on, hand, right? Hand ons, like you didn't understand the basic, how you going to become an accountant? How you going to learn it? So it's the same like math, and in most of the course, you have to know the basic foundation and know it in the right way first, right? Not miss it, not misinterpret it, and 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 then once you're already at the expert level, you can creative and make it more beautiful, just like ballroom. You have to know the step, what 2, 3, 4, 1 for cha-cha-cha before you can fantasize any fancy step and perform beautifully on the floor. In music as well, if you don't learn the basic one, do, re, mi, fa, sol, la, si, do, how can you put them become a composer, composed of the song of beautiful with beautiful lyrics, right? So everything you have to know the foundation, and math is a difficult subject. So only learning the foundation of it, it takes all the way from math, what uh, elementary to high school already, to even to university. Then after that, when you go to PhD or master, whatever, I don't know, then you can create in math. I have no idea. Maybe at that time you become a scientist or became a mathematician or whatever, like Albert Einstein. but for us, our common student, normal people, we would like to have a structure the foundation, a good foundation in mathematics, so that we obtain the right tools. And then from that right tools, we use it. We apply to all of this solving problem like this. And without the instruction in instructional teaching strategy, and I figured out like the United States, like our North America education, we try to change so many methods of education. We change from constructivism, we say, do not memorize what we call traditional routine rules, right? But to be honest with you, without this traditional routine rules, we just like, huh, what we are talking about. So, right? So I am the person who not like against any teaching method. Any teaching method is beautiful and have its own purpose, and we need to select it and combine it and teaching in the right way. So if I am teaching in the classroom, one day I will have to explain the lesson, the concept. I use instructional teaching method. The other day I use group work. I use like constructivism when we're doing the project or whatever. But we only can complete our project if we already learn the content and the concept. Then we put together, apply to do our project. But we cannot just go in and do project in math without any understanding about quadratic function, equilibrium system, calculus, like some depend on the curriculum, right? And topics we learn. But I mean the basic we have to learn first, from the teachers, from the friends or whoever um, understood about that before us to teach us. Then we absorb it and we use it. And it's up to us. We can be creative. I didn't stop you from being creative in math, right? However, we have to have a foundation first before we do our creative, put them in music, poem, or whatever. But we cannot um, try to construct the math in the wrong way, because math is only have one answer. You cannot provide like so many different answers and say, oh, they are both acceptable. There's no such thing like this in math, right? Um, so math is different from language course, absolutely. And so in this video, I show you how to do this problem, and I explain my idea. What do I think about the teaching in mathematics, to give you some more thoughts about our learning and teaching, and nothing wrong with that. We learn from each other, we share our ideas, and we whether we agree or disagree, but we listened and we figure out we accept it or not. It's up to us. But um, because I have been in this teaching is more than about 13 years, that I haven't included when I was in my back home. I already was a teacher. Um, so I did not count those years. Um, 13 years is my years in teaching in our North America, including US and Canada. Anyway, I hope you enjoy my video and my talkative. Forgive me about that. And I hope you enjoy my video. So thanks for watching, and stay tuned for our next video. We'll be getting into a more concrete example and apply to the equilibrium system we learned today. And our next topic in the unit 2 of our course Introduction to Calculus, course 2, I will explore with you together about iteration, which is you already learned it a little bit basic, like antiderivative. We just add more into it. And the next topic will be area under the curve. the second fundamental in principle in calculus. So thank you for watching, and bye for now.